From now on.
That was it.
No. You're on a timeout. 5 minutes in the penalty box, no talk.
Please keep that.
So in this,
Time out.
we've now found the initial velocity of the x and the initial velocity of the y. So in this, we've broken this vector into its component vectors. The reason this is important is because we now can use the information with the component vectors, and we, just like with force, we can find things going on in the x direction and things going on in the y direction. So this is like where all this is coming in at. So y'all remember x final equals x initial plus initial velocity times time plus 1/2 acceleration times time squared. There's a reason that you guys seen me whenever we were doing one-dimension motion. I would go from this, and I did that for x direction, and if we was doing y direction, I did y final equals y initial plus initial velocity times time plus 1/2 acceleration times time squared. And I know a lot of times that acceleration here was gravity, but it's not always going to be that.
Knock knock. Have some extra Chromebooks. Do you need any for in here?
We'll take some.
You can just add them to your inventory and store them in here.
If you want me to.
It's up to you.
It's whatever y'all want me to do.
I had a whole cart full. People have taken them. If you want them,
Oh,
you have.
sweet Jesus, if they're taking them, nah, go ahead.
You don't want them?
Or about it.
Okay.
Oh.
You can play Minecraft.
We're on the physics problems and not Minecraft.
Hold on. We can have physics in mind.
Yeah.
So,
Education edition.
in this is the big component and the big difference. The x direction can only have things going on in the x direction when we're
But
solving.
you can't just...
Y direction only has things going on in the y direction. Here is the key. What combines the two?
Velocity. And time. And acceleration.
Acceleration.
No,
1/2.
only one.
Acceleration.
All of them.
Acceleration.
Squared.
Time.
Time.
Because what happens?
Time.
Time in the x and time in the y is the same thing.
It makes us
You cannot travel longer in the x than you do in the y. You can't travel longer in the y than you do in the x. Time remains constant for both directions.
I wish.
Yes.
What if I throw a baseball, right?
Yeah.
Let's do it hypothetical, right?
Yeah.
I throw a baseball, right, and it starts rolling instead of like moving up in the air. Is that still moving in the y direction?
Now,
It would still be moving
No,
on the x
it is
plane.
not moving in the y
So
direction.
is that a portion where time in the x direction could be more than y?
You went from 2 dimensions to 1 dimension.
Yeah.
Okay, so that doesn't answer my
So what
question.
you can do is if you threw the baseball, this is literally what you're looking at. Whenever you have the parabola, until it hits the ground and starts rolling, that's 2 dimensions. As soon as it hits the ground and starts rolling, you have to break the problem in half, and from the moment it starts rolling, you're back into the 1 dimension in the x direction.
Okay, what
Unless
if
it
it asks me for the time of both x's added?
Then you will give it time for both x's added.
Okay.
Okay?
So,
Am I off my
but-
time out now?
No.
But,
Since that was a really good question, yes.
Thank you.
but why?
Okay.
But why wouldn't, if it was rolling, right? Why wouldn't that still be moving in that water?
Because you're not going
Because
up.
it's
Is it
only moving
moving?
in one direction, so it's not.
If I roll the ball, is it moving in the y direction?
Oh, it's moving in the x direction, okay.
Yeah.
Depends on how you
So,
orient yourself.
wait. So then do you have to change it from a y to x?
Yeah.
That was good. That was good.
You can use information from the y to find time to relate to the x direction, or stuff from the x direction, find time to relate it to the y direction.
Are you curious?
No, I'm not. You're back on a timeout. Just stop.
Sin
Wait,
bin.
am I on time?
Into the sin bin, boy.
Dude.
Into the sin bin.
I don't know. I just turned back there.
Connor was stretching back.
I was stretching.
And he grabbed him and popped his back, and Connor goes, "Oh, that was good."
Oh no!
I I vote Connor on timeout this time.
Time out.
No, into the sin bin.
Go.
All right, so in this case,
The sin bin.
I want to really look at the situation. So you guys should be kind of familiar to this. There's certain situations. So we're going to draw out.
Oh, you started on that now?
Oh my god.
You even had a line to follow and it's still not straight.
Dude, that's out
red
of
line
hand.
right there. This is whoa. Oh,
That's-
Connor's back.
Nobody cares if it's straight.
I swear that's Connor's back right now.
All right, so
Not that good.
Nobody cares.
it's a sunset.
How in the world is Jeremy Gibson?
not really.
Tyler Good.
All right. So here, for example, is
It's a rainbow.
Are we making rainbows?
Hey, you're the one that said if it's
Hold on.
okay if it's not straight.
Speaking of rainbows, Israel long last name,
what's happening. Y'all in first period, I couldn't get nothing out of y'all. Y'all come in 6, and it's just like y'all are just like
It was just
drank like 4 bags of huge
Yeah, I can
monster
say
Red
what I
Bull,
said.
crushed it,
there.
and y'all jacked up on Mountain Dew. And y'all just, you are now in the timeout box. Just stop. Yes, you. Yes, you. You didn't say anything, but you were thinking.
into the sin bin you go.
Just stop. You're in a timeout. You're in a timeout.
Ow.
Penalty box.
Oh my god.
You're not allowed to talk in the penalty box.
5-minute measure for fighting.
Oh my gosh. Okay, anyway, so in this case, here is the path. It has a special name called a parabola. This is the path that things travel whenever you throw it. So if you threw a baseball, you threw a football.
That's not always the path it travels. It can go up.
Okay, Connor. Yeah.
Anyway. No. Like in softball, you have a visor,
Penalty box. Timeout.
so it goes up instead.
Do it. Timeout.
She's cried.
I can do
You
timeout.
are now in the penalty box.
Sin bin. Yeah.
So in this, whenever you're looking at two-dimensional motion problems, there's one thing. So
Why
what
do
was
we
the
like
key?
this?
What connects them all together?
Time.
Time. So we're going to look at time, but in this case, in this parabola, there's 3 different spots of time you can look at.
When you throw it,
So time 1, when it's being thrown,
when it lands,
When it hits the peak.
the highest point
the zenith.
of the parabola.
The what? Zenith.
Highest point of the parabola, that's time 2. And then here, like whenever it touches the ground, or time 3. That can be different. It also can be like a different height. So,
It was something with an
okay, so in this,
I'm sorry. We're talking about the peak of the thing, and he's trying to tell me it's a different word, but it's not. He's in timeout and he's talking. I vote 10 more minutes.
you're in timeout, you're talking.
No, you let me out.
5-minute.
After the question, you
I
let
let
me
you
out.
back in.
No, I was never aware of this.
It doesn't matter. Just because you broke the law and are ignorant of the
It's been a
law
long
doesn't mean you
week.
didn't break the
Funny
law.
video Friday.
Y'all are making a funny video.
Tech day.
Okay. Alright, so in this,
And
we
then
break
what-
it down. Okay, you got time 1, time 2, and time 3. These are all important aspects because of different things that we can pull from it. So, for example, let's look at time 1.
So that's the Y direction, right? From time 1 to time
This is
2.
Y and X.
Y. Yeah, that's Y. Oh god.
This is combined.
Is this one of the things where we're gonna have to like flip it?
Couldn't we put time 1 as time initial?
You could.
And there you go.
Okay, and then just
I'm not labeling this time initial because you can, like what I'm literally going to break down in this is there's going to be a time initial
okay.
and stuff like that.
Okay.
Is this gonna be one of the ones where we gotta like move the graph to make an X?
You're going to break it. Okay,
So do I have to
okay,
move?
like when you look at this path,
Split it down the middle.
So,
My apologies. I do have some senior night parent tickets down here for the students that did not pick up their tickets for their parents this morning. Mackenzie Bledsoe, come to the office.
Oh, that's it.
Alright, so in this case, this is going to go like, if you did this, like in this scenario, if you broke it down into X and Y components, and we just slowly looked at the X direction, you're going to see the graph's going to travel like this. It's going to follow a straight line, not my line, because it's been mentioned that it's not straight.
I think you made a rainbow.
But you are going to follow a straight line in the X direction. The Y direction, we would also see a straight line. Not my line! Because it's been pointed out that it's not straight! But we would see it go straight up! And straight back
I
down!
can understand there because there ain't no lines to follow, but with that red line and the blue lines, actually.
You had 2
You're in
lines.
timeout.
You
You're in timeout.
2 guys.
Shut! Josh, you're in timeout. I don't care.
I was in timeout
So,
for 5 minutes though.
Looking at time 1,
you're back in for 10.
okay? So let's say, like this right here,
You get thrown off.
when you look at this,
2 major.
what are you doing?
That's a little peculiar.
I'm convinced that you went and bought those monsters. I'm absolutely
Thomas is sitting back there like
I'm convinced you signed out at lunch, you went and got some monsters, and you came back and you said,
That's
hey,
actually
Mr.
not
Ross,
allowed.
physics class, let's all get just ready to go for physics. Let's crush these monsters.
I've only said one thing this whole class.
Timeout.
And it contributed
It's
after
contributed to
dark.
the conversation.
Alright, so let's say we're looking at this situation here, okay? And let's say we just take the situation we was looking at. So, Connor throwing the football.
It wouldn't, listen, it wouldn't go that high or far.
Oh,
Excuse me.
So, we have the initial velocity is equal to
That's why
5
we
meters per
started.
second. So now in this, hold on, I gotta look here.
Is the velocity initial?
So we have the Y direction.
So, in this, right, where you say we're breaking it up, is there going to be like stuff like, say like, we're going to be doing 3 things, right? Like the peak, before the peak, and after the peak.
What's the why is there?
It's like I really can't narrow it down to that.
Okay,
We
well,
need more than 3.
Okay, so basically, right, we're going to have like a bunch of negatives and positives we're going to have to keep up with, right?
Yeah, right.
Well, it depends on what you
There's a
think
lot of
is
stuff to keep
initial
track of. Let's say that.
And so
There's a 90-degree angle.
I think we should establish on that board what is always negative.
Whoa, we ain't gonna establish what's always negative. It's always change things. Sometimes I want different directions to be negative.
Okay, but then you can specify that.
Exactly.
Well, why can't I just specify it on every problem?
Because,
So that I can establish my reference points so you know my reference point.
no, I'm saying,
That don't make things
Like when you-
hard.
May I ask, why, what's the NO?
It says velocity.
Today is not the day.
Tell my wife no cookies.
Hey,
come on now.
Hold on
I'm working
now.
hard for those.
Y'all give me a headache.
Want some ibuprofen? I ain't got any. I don't have any because you can't carry that in school.
That's illegal.
There you go. Sorry that looks like an N. That's supposed to be initial velocity.
Okay.
Velocity.
So then we have the initial velocity in X and the initial velocity in Y, which we broke all that down on that previous problem, okay?
Yes, sir.
So it's just kind of combining things together. So like at this point, whenever we're looking at this, so we're saying the ball just left Connor's hand.
There's 3 velocities.
Yeah.
Yeah, there's an initial velocity, which is what we like to call the resultant vector, the initial velocity in the X direction, which is a component of the initial velocity or the resultant vector, and then there's initial velocity in the Y direction.
So
Because what are we doing? We can't deal with things in both directions. We have to break them apart and deal with them in one-dimension parts and then join them back together using time.
So with this, do we need to get an angle? Or is that...
Oh
like,
yeah, I'm sorry. I didn't put that in there. What was it? That's 37, wasn't it?
37.
Okay. I just didn't know if that was something like we'd have to find or...
Sometimes I will ask you to find it, but you'll be given the information. So that
Okay,
you
what
can-
would that?
Yeah, like what would you use to find that?
So like I could give you like one side. You'd have to find the other side of a triangle, and then you got to find the angle. Like off the top of my head, I don't know why, but this seems familiar to me. That like what I like to do, and I could be wrong. Like I could change it up, but normally you're going to use the inverse tangent function.
What is that?
Because I'll get
We didn't have trig.
Yeah.
okay. So like on your calculator, you got your calculator.
Yes, I did.
So you see like your trig functions here. So like the sine,
Yes.
cosine, and tan.
Yeah.
Mm-hmm.
You see right above it what's in blue.
Oh.
That's the inverse function.
Okay.
So if
A
you
derivative.
get second and
Isn't
inverse
that called-
function,
Isn't that called cotangent?
Yes.
no,
Is it
no,
the
no, no, no,
derivative?
that's something different.
Is it the derivative?
No, okay.
I thought
What this is, it's like, so you know how normally we'll hit sine and put in an angle?
Uh-huh.
This is the opposite of that, so that we can find the angle.
What?
So what exactly would you
Whenever we do it, I'll
Okay.
work you through. It's literally, it sounds like the only thing you guys didn't get to see.
We didn't get to see a lot of things.
Mr. Hall, is that your car?
No, my car's not that nice to beep like that.
I apologize.
It would go.
It's okay. No, y'all would walk up to my car and it'd be like somebody would kick it or try to break into it, and they'd go, "That's the best you got, please." I seen worse than that last year.
literally my car?
And my poor
Did
little
something
car.
happen last year?
My car has been through the ringer. Hey, I'm gonna tell you this right now. Anybody wants to talk smack about a Chevy Cobalt, I'm gonna look at them and say, "Y'all lost your mind." I put that little Cobalt through the ringer, and that thing's still going.
I thought it was an Impala.
My wife has an Impala. I have Cobalt.
What color is your cobalt?
Cobalt's black.
Oh. What's his
Okay.
name? Or her name?
Their name. What's their name?
I hadn't named it actually.
Huh? Really?
Kobe.
You always name your car. Come on.
So,
Kobe.
Cobalt.
in this case, time one. Okay, so in this case, what would time be equal to?
0.
This is right when the ball leaves his hand, and we're going to say 0. Now, this can change. Okay, just hear me out. So we're just saying right here at time 1, at this point, time is equal to 0. Then we have different things going on. So in this case, the initial velocity, but remember, you can't solve it combined. What?
So,
No, is that initial time? Is that time initial?
Yeah, you can make it that. That makes you feel better. There you go, boom.
okay, so, like, if the problem says, like, let's say, for instance, Connor throws the football right, but he, like, takes 5 seconds to load it up so he can throw it that far and still won't get it there. But, let's say he takes 5 seconds to load it up, right?
To load it up.
Does that become that time 1 right there? Or is that...
No, because
Out of
the
the
whole
way.
time, that like, we can't look at that
Mm-hmm.
unless we have like sensors on him that's recording all these calculations at precise moments.
And it's
Because,
just
okay, it's like when Connor has the ball and he pulls back.
Mm-hmm.
that doesn't count.
Through this whole thing right here,
Mm-hmm.
there's different accelerations. Because you got to think about him as a point.
Yeah.
Here, he's accelerating,
Uh-huh.
but then he starts decelerating it. And then there's a point to where he's
Stop.
going to throw the ball, and he's
Okay.
accelerating it all the way through.
Speaking of throwing
But then
the
there's a
ball,
point whenever the ball leaves his hand, he no longer can act on it.
Okay.
At the point
So-
where he can no longer act on it, and the ball cannot be acted
it's
upon
measure.
by an external force,
Mhm.
that's when we look at it.
Okay,
So
so
by
if it
this-
gives me like Connor took 5 seconds to throw the ball, that doesn't matter in that problem. That's just there to throw me off or something.
You know what? I'm so proud of you, Logan. You did not take me for chemistry, but you're catching on really quick.
Thank you.
You're very welcome. Yes,
Still
that
have
means
an extra
nothing at all
question.
besides Mr. Hall threw it go, oh, time equals 5 seconds. No, it don't. Nothing matters in that moment because it ain't left his
Good
hand.
job, Logan.
Okay.
That's all fluff.
So I answered this question.
Why? You know, usually like if you just throw something like that, you're still accelerating. So why would? I don't know
When
how to
have
put
you
this in
ever
words.
just?
I know, but why isn't that like whenever you pull out, like you accelerate one way, then you got to decelerate, then accelerate another way? Why is that? I don't know how to word this.
Why is it not? Why are we not interested in it?
No, this is just a general question. It's
She
not
just said
really,
What's the point in it? Or?
like, yeah, kind of.
Okay, so
Because
think
if you're still
about
applying the
Yeah,
same force this way,
So
then
you
all of a
said
sudden
you-
here, why is
do
it
you
different?
do you do softball?
Yes.
Okay, so
Obviously,
softball.
look at her
If
breath
you're
up.
Yeah, look.
Oh wow. There you go. Okay, so you're playing softball. You're in the outfield. All right. You catch the ball. Are you gonna throw it like this?
No,
No,
what I'm
you
saying-
No. You got to get to home plate. What are you gonna do?
Well, yeah, I'm just saying, like,
You're
why
gonna pull
is
it back. Why? This is the reason why. You're
You can
pulling it
build
back
your accelerator.
Momentum.
so that you have a longer distance and a longer lever arm, so that whenever you're sending it, you can add more force to it. Because what's force equal to? Mass times acceleration. The ball's
That's
mass
also-
doesn't change.
That also.
I want it to get there as quickly as I can. So in that point, you can accelerate it faster because of faster lever arm.
It's just weird to think about, though. Like, hearing
This
it,
Like we
has
it
to
talked
do
doesn't
with
about
sound
with the
biology
board.
because your muscles, where your
Pushing from a
muscles
short
stretch,
point,
they
you can't.
Yeah, it's the
Long
same
point,
premise.
it's easier.
It's
Yeah.
your whole arm
We
is
should
just
should
a lever
show
system.
everybody that.
Yeah.
So in this, we have the initial velocity in the y direction. We're not caring about the initial velocity overall now because we broke it into the components. As soon as you got broken into the components, we don't care about nothing else. So it's equal to 3.0091 meters per second. We also broke up the x component, which would be equal to 3.9931 meters per second.
Hold on a minute.
Yeah.
Shouldn't the first initial velocity be like in the y direction?
Why?
Oh yeah, sorry.
void.
Void.
Good catch. Alright, so now in this, there's other components we can look at. So, a great example is, what is the acceleration in the y direction?
Hey,
3.00. Oh, sorry.
Acceleration in the y direction.
hey. So acceleration in the y direction, that
That,
would
it's up.
be gravity.
No, it's
It's up.
But if these are 3
Technically.
It is gravity.
yeah.
This is why. So in this point, this is where it comes down to making sure you have your reference point in your mind right. So right now in this case, I have this initial velocity going up. I have it as positive,
Yeah. Negative is
which
bad.
means coming down has to be negative.
Yeah.
Going up is positive, down is negative.
Yep.
So in this, how is gravity acting? Up or down?
Down.
So it must be
Negative.
negative 9.81
Wait,
meters per
why
second.
exactly
squared.
is it gravity?
Because what happens whenever you
It's
throw
on the
something in the air?
y.
What acts on it?
Gravity.
Gravity.
Oh, okay.
That's
okay.
what makes
Never
it
mind.
not go as
Yeah, you're
far
fine.
because Connor's not
So,
as strong as gravity.
So in this, now I'm going to pull on you for a minute. What's acceleration in the x direction?
Gravity.
No.
Friction.
Friction is a force,
It's your
not
force.
an acceleration.
So your
It's
acceleration.
in the x direction.
Wait,
The x direction. The ball has left Connor's hand.
It's
What made the ball move in the x direction?
when it,
Connor.
It was the force Connor applied to the ball
The
as he
net
was throwing
force.
it. So as soon as it left his hand, is Connor any longer acting on it?
No.
So there is no acceleration happening in the x direction.
Wow.
there's deceleration.
There's no deceleration.
It's
There's
constant?
nothing, there's no acceleration in that
Is it a
acceleration.
constant?
Unless you're talking about a rocket and we turn on thrust.
How, so it stays constant?
Well, it's gotta slow down by the time it's
Stays constant the whole time. What makes the ball stop? It either hits the receiver's hand, hits the ground. What determines whether it hits the ground or hits the receiver's hand?
Gravity.
How long it's going to go?
Gravity.
Gravity. Because your initial velocity in the y direction is going up. Gravity is pushing it down. So in that moment, what will take place is gravity will eventually
Push on it again.
stop the ball from moving upward,
Yep.
which happens here,
I just gotta say.
and start pushing it back down until it hits something and then a force acts on it.
So it would be
I finally got
applying
something.
downward rather than like.
Yeah, there's no acceleration in the x.
Okay.
There's acceleration in the y, but not in the x.
It's a
I
constant.
think I'm thinking too much.
Are we gonna get to a point in this class to where we have to calculate like wind resistance and all that
No,
garbage
in
too?
this class you will negate that.
Thank God.
Okay? In this case, you also can add some other pieces of information.
Did you know that if my major
So,
was physics and
for
give
example,
me $10,000?
Huh?
what would be the initial position here in the y direction?
That crap. I can't
Zero.
do this.
That's very smart of you. Because when you're making it zero, you're making your I want to say vertex, it's not the vertex.
Literally, it's not yours.
Origin, point of origin.
Y-E-R. Your.
Turn on closed captions on this. Some redneck was talking, have no idea what was said. Okay, what about the x direction?
I swear.
0.
I turned on closed
That's smart.
captions.
Because whenever you do that, what happens? You have now set this
It's completely different.
as a point of origin. It gives you helpful information. Now the key to it is, you have to stick to this. You're going to have easy problems to where this height and this height is the same.
Yeah.
You will also have hard
Wait.
problems to where this height is where you start, but you end here.
Oh.
Whenever that happens, you have to take the difference in height into account.
Delta Y.
So Connor's throwing the ball to Mike.
So,
In this,
Not Tommy.
uh,
I ain't throwing the ball.
Mr. Ross,
yeah,
whenever we do the difference in height, is it gonna be like just a straight line? Or is it gonna be like kind of like a curved looking thing?
you're still going to do the same thing. Like overall, it's going to be a curve, but then it's going to stop like here.
Okay, but like on the bottom, is it gonna be like
The
it
X,
stays straight and then it'll jump up to where it stops, or is it gonna go straight line?
if you're looking in the X direction, it's just going to be a straight line. But then if you're looking at the Y, it's going to go straight up,
Mhm.
it's going to come down, but it's going to stop before it hits the point where it started,
Okay.
which matters.
Okay.
Okay? Alright, so let's look at time 2. Here at time 2,
Not this.
you have a time.
That's concerning. You went, whack.
In that time, you can solve for it, but you're not going to know what it is.
Mhm.
In this case, you can break the problem in half. Sometimes in physics, it's easier to break the problem in half to where you look from going from T1 to T2, and then from T2 to T3. So you're looking at half the picture instead of the whole picture.
And then you
Wouldn't
can
it
piece them
be
together.
easier to do like T1 to T3 and then
In some cases, yes. There's different scenarios. This is where physics gets very fun.
Is this
Because
Miss
it
Cole's fun,
opens
or is
the
this our
world up for what you can do. Yes.
Is this Miss Cole's fun, or is this our kind of fun?
This is Miss Cole's fun on steroids.
Okay.
Like,
Whoa now,
I'm
buddy.
waiting.
Whoa.
I'm waiting for us to be working a problem in here, and Miss Cole's just going to bust through this wall like the Kool-Aid Man. Oh yeah! Oh yeah! Miss Cole, you have gotten so tall.
And
When did your video?
I ain't doing a video. Why? Because I done one for cross country. I ain't doing one.
Well, then send that one over to.
I don't know where that one's at. I ain't doing one.
Oh my goodness.
Mr. Hall's that video?
Yeah.
Yes. No.
Hey, are they coming after school?
All right.
He's not
So
allowed.
After school.
He's not allowed. Sean.
What?
later. So time. You can solve 4. This can be solved at T2. In this case, no.
Yay!
Yeah. Oh yeah.
All right. You get a break till Monday.
Thank God.